Hello statisticians, today we're going to do a chi-squared test for goodness of fit. Here's how it works. So, first thing, let's recap chi-squared. We know on our formula sheet for AP statistics, we have that chi-squared is what we get when we take our observed values minus our expected values. We square that difference, that makes all of our differences a positive value. And then we divide by the expected number. If you add up each one of those for each of your values, you get a chi-squared value. The chi-squared distribution is based on these expected counts. To get the expected counts, you take the sample size times the proportion of success for that particular category. So I have like PI here for like the first category, the second category, the third category. You do it for each of those. Chi-squared distribution is skewed to the right. If you get smaller chi-squared values, that means that your observed minus expected were small numbers. So that means that our observed values were similar to our expected values. A larger chi-squared value means that our observed values may vary more from expected. We have a larger difference right there. So as the degrees of freedom increase, remember our chi-squared distribution, which is right skewed, becomes more and more symmetric. And ultimately, when we're talking about a p-value for the hypothesis test that uses chi-squared, we're talking about the probability of getting a chi-squared like ours or more extreme if the null hypothesis is true. So all those p-values are conditional probabilities basing the idea of your null hypothesis is true. Here's how likely it is to get expected values like, observed values like ours, if the expected values are in fact what we think they should be. So the chi-squared value would be the border on that curve. And then the p-value is the probability of getting that chi-squared value or more. So a goodness of fit test, what we want to look for is a chi-squared, you have one population of interest and you have one categorical variable. So you have one population and one question you're going to go ask from that population. Usually we're talking about a distribution, meaning a whole bunch of proportions, of several hypothesized proportions, a distribution that adds up to 100%. So instead of just talking about one proportion, the proportion of orange, we're talking about how many are orange and yellow and green and purple, all of those as proportions. Sometimes you will have a stated set of proportions that add up to 100%, like 20%, 30%, 40%, 10%, or sometimes you may have an implied distribution of those proportions. Implied could be things like the problem says uniformly distributed across all 5 categories, which means that each category would represent 1/5 or 20% of your total. You might say something like, the people had no preference among the 3 categories. No preference would mean that it would be equal percentages of each category, which would be 1/3, 1/3, and 1/3. Or sometimes you might see something like a ratio. The ratio of men to women to children was 3 to 2 to 7. The best thing you can do on something like this, pull out those skills from the SAT and say 3 plus 2 plus 7, that's 12 parts. And so men are 3 of the 12 parts, 25%. Women are 2 of the 12 parts, about 16%. And children are 7 of the 12 parts, about 58%. So again, you may have your proportions stated in the problem, and sometimes they're implied. You have to figure them out yourself. So phantoms works the same as always. We're going to define the parameter first off. Since we're talking about proportions and we have several, that means we're going to define several. So let P sub 1 be the true proportion of the population of whatever that are something. And you're going to repeat P2, P3, P4 for each category of your categorical variable. Like let P1 be the true proportion of all Skittles that are red, and P2 the true proportion of all Skittles that are orange, the true proportion that are green, etc. All the way down, one for each of your colors. Alternately, if you don't want to write that down for every single one, there are some other options. My favorite is this one. Let P1, P2, P3, P4, and P5 be the true proportion of all Skittles that are red, orange, green, purple, and yellow, respectively. Respectively means that the numbers should match up. P1 goes with red, and P2 goes with orange, P3 with green, P4 with purple, P5 with yellow. So respectively, the order I listed them in 1, 2, 3, 4, 5 is the order they match up color-wise. You could also just use context, probability, or sorry, the proportion sub-red, proportion sub-orange, etc. And a lot of people would recommend that you do this because it helps you remember what you're talking about. Just remember that if you are going to use a variable notation of any kind, like a p or a mu in any hypothesis statement, you should always be sure to define it in context just to be safe. So H stands for hypotheses, so we're going to state the hypotheses for a goodness of fit test. Now, for a goodness of fit test, basically we're saying, I think my hypothesized proportions are as stated. So going back to that, uniformly distributed over 5 categories, 1/5, 1/5, 1/5, 1/5. My null hypothesis might mean that P1, P2, P3, P4, and P5 are all equal to each other, and they are equal to 20%. And then for our alternate hypothesis, we would say at least 2 of the proportions stated in the null hypothesis are incorrect. Well, why at least 2? Well, if they have to add up to 100% and you increase 1, you're going to automatically decrease at least one of the others. So you can't have 1 be incorrect. They will always be at least 2 that are incorrect, and maybe more. Okay. Another way, if you have a specific distribution, for example, P1 is 0.125, P2 is 0.125, P3 is 0.25, and P4 is 0.50. So based on the ratios or based on some sort of stated proportions, you know what each of these individual ones are supposed to be for the population. And again, your alternate hypothesis is going to say something like at least 2 of the proportions stated in the null hypothesis are incorrect. It's okay to write them in context. For example, the distribution of color for all M&Ms is the same as the claimed distribution. And the alternate hypothesis would be the distribution of color for all M&Ms is not the same as the claimed distribution. So if you have a stated distribution from the M&Ms Corporation, like we did in some of our previous activities we've done in class, you could say it's either the same as what M&M says or it's not the same as what they say. And then something else you could say would be like the sides of Carrie's die are equally likely to show up. So if I'm talking about a weighted die, like in one of the problems the other day, and we think the die might be weighted, my null hypothesis is that each side has an equal proportion of times it should show up, 1 out of 6. Okay, the alternate would be that the sides are not equally likely to show up. Okay, assumptions for inference. Now, the assumptions start off pretty much the same. We have randomization. Your data should be collected through a random sample or a randomized experiment, same as all of our previous chapters. 10% condition. If you're sampling without replacement, you need to make sure that your sample size is small compared to your population size. Specifically that your sample size is less than 10% of your population size. So that's without replacement. So if Carrie is rolling her die, you don't need to check the 10% condition because every time you roll a die, you're sampling with replacement because every number has a chance of coming up again. If you are sampling from a big population and you're not allowing for repeats, that's when you need to check that 10%. And if you happen to be in a problem dealing with an experiment, if you have random assignment, that's not the same as random sampling. So you wouldn't need to check it in that case. And then finally, we have our large counts. Now, unlike other tests of proportions, the ChiSquared goodness of fit test, what we want to check is that all expected counts are greater than 5. So that's a little bit different from what we've had in previous chapters, where for the sampling distribution for sample proportions, we wanted our NPs and N times 1 minus Ps to be greater than 10. In this case, what we've got are greater than 5. Okay. Okay, so on our assumptions, what would that look like? So you open a bag of Reese's Pieces and find 36 orange, 15 brown, and 16 yellow. What are the expected color counts, assuming that Wikipedia is correct? So I've got my expected colors. We did this in the video from yesterday. First thing was randomization. We've got 10%, we've got large counts. So I would write down, well, it doesn't say that this is random, but I am talking about a bag of Reese's Pieces that I'm assuming could be considered a random sample of all Reese's Pieces. So this bag was bagged at a factory somewhere that it could be considered a random sample. 67, which was my total, that would be less than 10% of all Reese's Pieces. I think that's very reasonable. And then all expected counts greater than 5. Now I've got the work shown. I showed where I got those expected counts. So I showed actual numbers. 67 times 0.5 is 33.5. 67 times 0.25 is 16.75. I've got the work shown and I've got them actually written out for each color category. So yes, all expected counts are greater than or equal to 5, and you can see those counts checked in the table. All right, now I need to name the inference procedure. That's going to be a chi-squared goodness of fit test. I'm going to write down the test statistic. That's going to be a chi-squared value and the degrees of freedom. Remember, degrees of freedom in a chi-squared goodness of fit test is k minus 1, where k is the number of categories. And I'm going to obtain the p-value and write it down. So just the same as some of our previous chapters here. So in our problem, when I go to put this in my calculator, I have my chi-squared goodness of fit test. I run the observed and expected counts, and we're going to go through how to do that exactly in a minute. And I'm going to read these numbers right off of my calculator. My chi-squared value is 5.0667. I've got 4 degrees of freedom because 1, 2, 3, 4, 5 categories. 5 minus 1 is 4. And my p-value, again, I'm reading right off my calculator, is 0.281. So I'm going to physically write those down. Don't just leave them in your calculator. Okay, and then we're ready to make a decision and state the conclusion. So remember, the first statement is always regarding the null hypothesis. The second is always regarding the alternate hypothesis. In the first statement, you always want to make sure you state the linkage to the p-value and the decision that you're going to make. So option 1, since the p-value is less than alpha, there's the linkage, I reject the null hypothesis. That's the decision. Now my conclusion, that means there is convincing evidence to show whatever ha was. And you always want to state that statement in context. Okay, option 2 would be that since the p-value is greater than alpha, I fail to reject the null hypothesis. That means there's not convincing evidence for ha in context. So in our bag of Skittles example here, we got a p-value of 0.281. So that 0.281, that's a very large p-value. So what we're going to say is since the p-value is greater than alpha, 5%, I fail to reject the null hypothesis. So in this case, that means there's not convincing evidence for ha. My null hypothesis was that the distribution of Skittles was uniformly distributed by color. That is, Skittles says that there's 20% of every color. They're uniformly distributed. There's not more of one color proportionally than there is in the other. But my p-value is saying, nah, you could get results like this even if they weren't different. So there is not convincing evidence to show that the distribution of colors for Skittles is different than the company's claim. Okay, so first example then. A marketing analyst wishes to see whether consumers have any preference among 5 flavors of a new fruit candy, Star Sours. A random sample of 100 people who purchased Star Sours were asked which flavor was their favorite, and the results were as follows. Cherry, 32, strawberry, 28, orange, 16, lime, 14, grape, 20. Perform a hypothesis test at the 5% significance level to see if there's a preference in the colors. So you always want to start off these questions, what is the variable? So the variable in this case is, what's your favorite color of, or what's your favorite flavor of Star Sours? Okay, favorite flavor of star sours. That's my variable. I'm asking this of people who recently purchased the star sours. So that's going to be my population, all people who've recently purchased the star sours. That variable is categorical, by the way, which means I know I'm going to be in some sort of proportions type test. Okay, what does it mean to have no preference in terms of proportions? Well, if I have no preference, that means that the preference of flavors should be equally distributed across all of these categories, uniformly distributed. No preference means one flavor is not liked any more than any other flavor in general. All right, so my null hypothesis and my alternate hypothesis coming up, but let's phantoms through this. So let P1, P2, P3, P4, and P5 be the true proportion of people who have recently purchased star sours that prefer cherry, strawberry, orange, lime, and grape respectively. Okay, so that is the P of phantoms, my define my parameter. Now, the reason why I decided to put them in that order was because that is the order which they were listed in the problem. The second thing I'm going to do is I'm going to state my hypotheses. So I have two hypotheses in this case, okay? My null hypothesis is that there's no flavor preference, which means that the proportion for each of these flavors is equal. And since there are 5 flavors, that's 1 out of 5 or 20%. And yes, you could just say 1 out of 5 there if you want instead of 0.20. My alternate hypothesis is that there is a flavor preference, which means that at least 2 of the proportions in that null hypothesis are false. All right, now it's time to check those assumptions. So my assumptions for inference here. Observed counts do come from a random sample. That was stated in the original problem prompt. Check. Is 100, which was my sample size, less than 10% of all people who have recently purchased star sours? I'm going to say that is reasonable to assume. I have no reason to believe that it is otherwise. My observed counts then. So I'm going to show the work. I have a sample of size 100, that's my N, and each of these proportions is 20%. So for each of these, 100 times 20% is 20. So what you should do is make sure you show that work, show that multiplying the number by the proportion. And then I want you to make a table. I want you to list out for each flavor, cherry, strawberry, orange, lime, grape, and you could abbreviate these if you wanted to. And then I want you to list both the observed value and the expected value. So my observed values were given to me in the problem. My expected values are all going to be 20 because 20% of 100, it should be equally distributed if there is no, uniformly distributed if there is no preference. So all expected counts greater than 5? Absolutely. And I've shown what all those expected counts are over here in my table. Now, the name of the test, we are going to perform a chi-squared goodness of fit test. A goodness of fit test is when you want to think about one variable and the distribution, proportionally speaking, of that one variable over one population is what we have. I need the test statistic, which is going to be a chi-squared. Chi-squared has degrees of freedom. We've got 1, 2, 3, 4, 5 categories. So k minus 1 gives me a degrees of freedom of 4, and I'm going to need to obtain that p-value. Now, I'm going to do this in my calculator. So here are those steps. So in your TI Nspire, the first thing that you're going to do is you're going to open a new document, and you're going to add a list and spreadsheets page. In that list and spreadsheets page, you're going to enter and label a column of observed and expected counts. And it's really important that you label which ones are the observed counts and which ones are the expected counts. You have to label those because in a minute you're going to have to choose which one is which. So I usually call them O for observed and E for expected. Okay, the next thing you're going to do is while you're still in this spreadsheet, you're going to go Menu, Statistics, Stat Tests, and you're going to choose number 7, the chi-squared goodness of fit test. The chi-squared goodness of fit test is the one that looks like GOF, G-O-F, goodness of fit. So I'm still in that same spreadsheet itself, but I've pressed Menu and then Statistics and Stat Tests, which I believe are usually 4 and 4 in this particular menu. When you press that goodness of fit test and you hit enter, it's going to ask you to choose your observed list, your expected list, and you're going to have to type in your degrees of freedom. So you're going to use those drop-down menus to select your observed and expected, but you're going to have to type in your degrees of freedom, which means you need to have thought about that before you go into this problem. For a chi-squared goodness of fit test, remember degrees of freedom is k minus 1, where k is the number of categories. After that, you are going to select OK. All right, so we've select OK, and it runs this test for me. Notice that the chi-squared value is 18, the p-value is 0.00, and I love this, 1, 2, 3, 4, but 0.001, and there's my degrees of freedom. So I'm going to write those down. So again, here's for the phantoms, the name of the test, chi-squared goodness of fit. The test statistic is that chi-squared is equal to 18 and the degrees of freedom 4, and I'm going to obtain the p-value, which is 0.001. I'm going to write those down on my paper. And now I'm ready to make a decision. Now, since that p-value is less than alpha, and if they don't give you an alpha value, remember you can set it yourself. Usually 5% or 1% is a good choice. So since the p-value is less than alpha, I reject the null hypothesis. So the null hypothesis was that there was no preference. The alternate hypothesis is that there was a preference. So I'm going to say that. There is convincing evidence to show that there is a flavor preference for star sours for all people who recently purchased this candy. All right, so example 2. Does the color of a car influence the chance that it'll be stolen? In a recent article, the Associated Press reported the following information for a random sample of 830 stolen vehicles. There were 130 white, 110 blue, 300 red, black 230, and other is 60. So if we just look at this data, it looks like, wow, there's a lot more red cars stolen than any other color of car. So does that mean that red cars are stolen more often than other cars are? So remember, it's not about the proportion, it's not about the raw number of cars, it's about the proportion. So we go to the BMV, and the BMV indicates that 15% of all cars, and I guess we're assuming cars that have registrations that can be driven on the road, are white, 15% are blue, 35% of the cars are red, and 30% of the cars are black. 5% are other colors. So not only were there more red cars stolen, then there are just more red cars. The red cars are just more common than any other color of car. So we're going to use a 1% significance level to test the hypotheses. Oh, look, see, typo. Okay, to test the hypotheses that the proportion of stolen cars are identical to the population color proportions. All right, so here's the idea. What's the variable? Okay, the variable is what color is the car. That's categorical, so we know we're in a proportions problem. What is the population? Okay, so we have taken a random sample of 830 stolen vehicles, which means that our population is representing the number of all stolen vehicles. All stolen vehicles. So what does it mean to have no preference in terms of the proportion, or what does it mean to have that identical to this population color proportions? What's going on here? So what we're trying to say is that we want to know, does our sample indicate that the number of stolen cars, that cars are stolen that are red, for example, if that's 35% of all stolen cars, then that makes sense, because if 35% of all cars are red, then we would expect 35% of all stolen cars to be red too. And if that's not true, then we think that maybe cars are stolen more often or less often based on their color. All right, so let's start off here. Let proportion sub 1, 2, 3, 4, and 5 be the true proportion of all stolen cars that are white, blue, red, black, and other colors respectively. You could also do subscripts here, but you're going to have to be careful if you try to abbreviate. For example, you can't abbreviate blue and black both as BL. All right, my null hypothesis is that the proportions of stolen cars match the proportion of all cars in that color. So for example, if 15% of all cars are white, then I would expect that 15% of all stolen cars were white if it doesn't make a difference what color the car is if it gets stolen. So the color of car does not influence the chance of it being stolen. The proportion of stolen cars of those colors match the proportion of all cars that are those colors. And my alternate hypothesis is that at least 2 of the proportions in my null hypothesis are false. Okay, so for example, if that 35% is too low and really lots of red cars get stolen, then that's going to make one of my other categories have to go down. All right, so the color of car does influence the chance of it being stolen. So if our proportions match the proportions of all cars versus the proportions don't match the colors of all cars. All right, assumptions. Observed counts come from a random sample. That is check mark. That was stated in the problem. 830, that was our sample size. That is less than 10% of all stolen cars. I think that's pretty reasonable to assume. Okay. And then my observed count. So I'm going to show the work. I only had 4 different percentages, even though I had 5 categories. I'm going to flip back really quick here. So 15% and 15%, those match for white and blue. Okay, so only 4 percentages to check here. Those are my n's times the p's here, and that gives me my expected counts. And now we're going to make a table and write all those down. So we observed 130 white, but we expected 124.5. Blue, 110 versus what we expected, 124.5. We observed 300 red, but we expect 290.5, etc. for the rest of the colors. Oh, and it looks like I have a typo here in one place or the other. Probably this one. All right. There we go. So all the expected counts greater than or equal to 5? Absolutely. So we will perform a chi-squared goodness of fit test. That's the name of our test. We need the test statistic with the degrees of freedom and to obtain the p-value. Now again, we've got 1, 2, 3, 4, 5 different categories. So that's why the degrees of freedom is 5 minus 1. And I realized on my examples today, I have 2 different ones with degrees of freedom 4, but that doesn't mean that it's always 4. Okay, so we're going to take, in our calculator, we're going to put our observed counts and our expected counts into a spreadsheet. Once you've got those in your spreadsheet, you are going to do menu, statistics, and stat tests. You're going to choose number 7, which is the chi-squared goodness of fit test. Okay, it's going to ask you what's your observed list name, so you're going to use the drop-down menu to pick O and to match that up, and you're going to pick the drop-down menu for expected to choose E. And you're going to type in that degrees of freedom. Remember, that is something that you need to know how to calculate. Okay, we're going to click OK. When we click OK, we end up with our chi-squared value and our p-value from that menu. All right, so my chi-squared value from the calculator was 11.939 with 4 degrees of freedom. My p-value is 0.0178. Oh, so again, that's the name of the test. That's the test statistic. We've obtained the p-value. Now it's time to make a decision. Now remember, our alpha value in this problem was stated that we were supposed to use 1%. So even though 0.0178 is really small, it's not small enough. So since the p-value is greater than our alpha level of 1%, I fail to reject the null hypothesis. That means there's not convincing evidence to show that the color of car influences the chance that it'll be stolen. We don't have enough evidence to show that, for example, red cars are stolen more often than they are existing in the general population. Okay, so other things that might show up here. So, and excuse my little writing, it's really hard to select all of these in PowerPoint to get all of the things to show up. So let's say that they give you a ratio and they say yes to no to maybe is 5, 4, 3. So again, what you want to do is take 5 plus 4 plus 3, that's 12 parts. So if I'm talking about those population proportions, the proportion of yes would be 5 out of the 12 parts. The proportion of no is 4 out of the 12 parts. And the proportion of maybe is 3 out of the 12 parts. And it's perfectly fine to leave those as fractions. You don't have to turn them into decimals. If you do want to turn them into decimals, please use at least 3 decimal places, if not 4 or more, if you have to round. Okay, but using the fractions are fine. For the expected counts, you would say, what are the expected counts for sample size 50? So again, I would take 50 times 5/12, and 50 times 4/12, and 50 times 3/12. And those expected counts, when you go to put those in your calculator, again, you're going to want to use at least 3 decimal places, if not more, for those values. Okay. Other things that might show up is if I'm given the chi-squared test statistic and I want to find the p-value associated with it. So either I've calculated the statistic by hand or they've given me the statistic as part of the problem itself. Chi-squared, for example, equals 8.58 with 6 degrees of freedom. So remember what this means, my chi-squared distribution is a skewed to the right distribution. Somewhere along that side, there's going to be my chi-squared value of 8.59. Okay, that was given to me. I know that this is a chi-squared curve based on 6 degrees of freedom. The p-value is the area to the right of that under the curve. So I'm going to, in my calculator, I'm going to go into a scratch pad or a calculator page. It doesn't matter, but just the scratch pad will work. I'm going to go menu, statistics, and distributions. This is the same chain of command that we do for norm CDF and T-CDF. So you're going to pick number 8, which is chi-squared CDF. It's going to ask you for the lower bound. The lower bound is going to be your chi-squared value. And it's going to ask you for the upper bound, which is going to be infinity. So I just type in 10 to the 99th in there, which is basically huge. And then you're going to have to put in the degrees of freedom of 6. Okay, when we do this, we end up with 0.197983 down here. That is our p-value. That is that area under the curve. So here's what you need to be able to do today. For one categorical variable from one population, you need to be able to determine the degrees of freedom for a chi-squared distribution. That means that's k minus 1, where k is the number of categories. You need to be able to calculate the expected values for each category. That's the n times p's based on those hypothesized proportions. Remember, sometimes those hypothesized proportions will be stated right out there for you, and other times they will be implied with words like uniformly distributed or no preference, or they'll be given to you as a ratio. You need to be able to compute the value of chi-squared test statistic by hand using the formula, or to be able to find it in your calculator after you've run one of those chi-squared tests. And then you need to be able to perform all the steps of phantoms for a chi-squared goodness of fit test. That includes those assumptions and conditions. What's coming up next? On the next lesson, we're going to talk about what happens when you have a two-way table. Or in other words, what do you do with one categorical variable for two populations? That's a test for homogeneity. Or you have two variables that you get from one population. That's a chi-squared test for independence. There will be some things that are a little different. In a two-way table, computing the expected values is a little bit different. And then with hypotheses and the names of the tests, those are going to look a little bit different for each one of these tests. Things that are basically the same, checking assumptions from here on out is pretty much the same. Expected counts have to be bigger than 5. We need a random sample. We need less than 10% of our population. Using the calculator is pretty much going to be the same. We're going to use our calculator to get all of these numbers from that we need, the test statistic and the p-value. Interpreting the p-values by comparing to alpha, that's also going to be basically the same. Okay, all right, so remember that you can watch this video again, or you can speed it up so that I talk really, really fast the next time. Please don't hesitate to ask if you have any questions.